Hello, everybody. This is going to be a quick video or not so quick video lecture on our Kamer counting assignment lab that's going out. And so first of all, this is the link to this lab. I wanted to start off by giving you the origin story where this assignment came from. The first semester I taught this class was the fall of 2016, and I just sort of made it up every day as I went along of what we were going to do every day. And people asked if we were going to have class the Tuesday before Thanksgiving, and I was like, of course we're having class on this, uh, this, like we're not going to miss out on the opportunity to do more things. And so as Thanksgiving got closer and closer, I realized that I was like the late Tuesday afternoon um, uh, class before Thanksgiving, and I was forcing all these people to stay and do this, so I like better come up with something good. And so I thought we could have a group project, and I paired people up who were going to be in town, and I was like, we're going to do Kamer counting. And this is a slide that I've updated a little bit. I've like put an origin story in this Wayback Machine thing, but basically I said, I introduced Kamer counting. They had never seen anything about it at all. We didn't do, the count lab at the beginning was not counting like adenines even. And I was like, okay, like just let us know. I tried to not have too much spoilers in it or explain how to solve the problem. And I had this like bonus thing of like, it may be unreasonable to expect you to get both of the things done in 80 minutes. That's fine. Like it's kind of laughable how ridiculous this was at the time. So let's talk about the Kamer counting assignment. We've done a bunch of things on it. You can think of DNA as a 4-letter alphabet: adenine, guanine, cytosine, and thymine, A, G, C, and T. And it's just a really long string. We discussed this before. This is sort of the pseudocode for how you count them. Given some length of a string, this is from Wikipedia, so theirs goes from 1 to n minus k plus 1 inclusive. We obviously do the exclusive from 0. But you build this and you basically count each one of them, right? And so, like I said, you've done a bunch of prep for this now. The first lab is nuclear-based counting, which has been put in to make this lab go well. Essentially, we could count anything at the beginning. It seems like let's get familiar with chromosome and nucleobases and dealing with that whole thing. We're basically counting Kamers of length 1. You built a Kamer counter already for the MapReduce assignment for the int count. And you also built a hash table map as a studio earlier. This seemed both useful for understanding how hashing works, and so it would help you with the matrix MapReduce assignment. But also we're going to build a thread-safe data structure in this lab, and so like building a non-thread-safe hash table will hopefully help you for building your thread-safe version now. Okay, a couple of quick things. These are the interfaces that you're going to end up implementing a bunch of things for. The one on the top is a Kamer counter. You're going to be passed a list of sequence and some K, and you're supposed to return one of these Kamer counts. I've built all of these, but they're basically a way of making it so that you can return something where someone can both iterate through all the Kamers that you found and look up the count for it. If you think of DNA as represented as this big long string, Kamer counting is sliding this window. So this would be counting the 5 MERS in this chromosome data right here. And you slide this window over one at a time to count them all. And so in this thing, you can see that ATCGG has shown up twice. That is fundamentally Kamer counting. I shot a video on this subject. It actually counts SARS-CoV-2, which is the virus which is causing COVID-19 right now, the disease. So I encourage, if you haven't watched it already, I encourage you to watch it. It sort of goes through at a high level, like how you would approach sort of using Kamer counting as a way to try to find some interesting aspects of something like a novel virus that shows up on the scene. And so there's that. There's also a string hash map demo that sort of just takes you through the warm-up of how to build the very simple Kamer counter that keeps track of the strings of the, keeps track of the kamers as a string, and then uses just a hash map to keep it. And it's a sequential program, and it's all good. Then I basically build a broken version of a concurrent hash map version where we're going to parallelize this this process, and we're going to use concurrent hash map to, which is a thread safe map, and that's going to be part of the puzzle. And the other part of the puzzle is to use the compute method. And if you watch these two videos, hopefully that will clear up a lot. And this one does just tracking all the locations that bears have gone to, but it's just a way to show off how to use concurrent hash map and compute to solve, to make things both. The concurrent hash map gets rid of the data races, and compute gets rid of the atomicity race. So let's sort of talk about what are some other representations that you could store it. So this is keeping a string for every kamer. That's using up a lot of memory. Can be optimized a little better. So I want everyone to think about what are the different data representations that you could use if, say, you were counting the 3 mers, or the 12 mers, or the 23 mers, or the 2000 mers. And so if everyone can just pause the video and think about what your answers are to those questions. Okay, so we're back. So let's talk about a couple of these things. First of all, if this is this big long string and you're keeping a byte for every character, or let's say it's a Unicode string so that you're able to sort of support languages other than English, so Cyrillic and Chinese and all sorts of wonderful, beautiful languages in the world. Sometimes you'll even use 2 bytes per character. So, you know, like you could have 2 to the 16th different representations. You can think of DNA, if you think of DNA as a number, it's basically a 4-letter alphabet. So you can, instead of using 8 or 16 bits per character, you can use 2 bits per letter, right? And in this case, you know, like what I've chosen is adenine is 0, T is 1, C is 10, or 1, 0, excuse me, and G is 1, 1. So 0, 1, 2, and 3, right? And now I can pack in the let's say this is a kamer, ATCG. I can pack that into 0, 0, 0, 1, 1, 0, 1, 1, and now it's just the number 27. Okay, and so probably the first, you know, serious kamer counter that you're going to build, part of the lab, is going to be the long concurrent map kamer counter. It's going to use a concurrent map. It's you're going to be passed a function so that you can create it, so that we can use create multiple different ones, just to provide a little bit of indirection so that we can test your bucket map that you're going to build, your thread safe map, and Java's separately. But you're just going to have something that goes from long, that'll be the kamer, to integer, which is the count. And this should work for any k less than or equal to 32. If you wanted to do like a 2000 mer, you'd have to use big integer or something like that. Or there's like bit sets, I think, or something that would be a little bit better. So I mean, you can do that. And so now let's get to these other questions, which is like, what would k less than or equal to 15 allow, right? And for this one, you can, first of all, you can fit it into an integer. So all of a sudden now, instead of having to keep 4 bytes, or excuse me, 8 bytes for a long in your map of key to, now both your key and your value could be an integer. But there's something we could do that would be much, much better. And I want you to think about what data structure is a lot like a map, right? And that you can look at things up, you can get the values, and you can set the values. But if the key is always going to be some value that goes from, say, k is 12, between 0 and 12 to the 4th minus 1, right? So it would fit in an integer. What's a data structure that would work for that? I want everyone to pause and come up with their answer. Okay, and now we're back. Hopefully you actually gave some thought to it and came up with the fact that then you can just store it in an array. I cannot imagine a faster way to build it than to simply pack this k-mer into an int and then use that as the index. So when you build this array, the index will be the key. That will be the k-mer, right? And the value at that location that you increment every time will be the count. And this will run like blazingly fast. The next one you're going to build is an atomic integer array k-mer counter. We're going to talk about atomics in the next lecture. So if we get to this point, you may want to wait until then or dig into atomic integer array. It's a Java concurrent. It's a standard feature. You can look up all you want about it. You don't have to wait for me, and just press on. So what I'm going to say is that one will allow us to do it in parallel. This will be unbelievably faster than using the concurrent hash map. We can use a concurrent hash map again with integer and compute. It'll work. This will be blazingly fast and work. Have even to the point of hardware support for just how well suited this is. I will say as a bonus, do not make an array of atomic integers. That will work, but it'd be much better if you just use this one class has been built for exactly this process. So definitely use that. From a motivation standpoint of why I like this assignment, just to we're sort of getting to the point where we're talking about is this is a real problem. You get a chance to build a thread safe data structure. We're going to use locks. I'm going to show that in a second. I can give an open-ended assignment for extra credit where you have to build your own atomic or optimistic concurrent data structure. You have to deal with contention, you have to deal with balance, and there's an opportunity for optimization. There's a lot of really good things about this. So let's talk about a couple of these things right now. One of them is contention. And fundamentally, if you make one data structure and it's a concurrent one, so you're going to make it thread safe, and then you release a bunch of tasks that all beat up on that data structure, or all are like just constantly trying to mutate and read that data structure. Hash maps have sort of this built-in relief of that contention, right? So isolated or locks or synchronized or whatever features we're going to talk about when or atomics that allow you to build thread-safe data structures. It doesn't help if you have a thread-safe data structure and everyone's just using it at the same time and you have a parallel program that turns into a worse than sequential program because everybody's waiting. But a hash map has sort of built-in contention relief. You can make it so that, in this case, there's 256 buckets. If you have a certain number of locks, let's say 256, although it doesn't have to be, and the locks protect a certain number of the buckets, while Lisa Smith is being added to 01, John Smith can be adding over here. Now, maybe Sandra D has to wait because you have a lock protecting these two, but Ted Baker can go in parallel and Sam Doe can go in parallel. So we're going to build a data structure that has a lock per bucket. It doesn't have to be that way. Seems like the easiest way to go. But if you think about it, the hash map data structure just inherently has some contention relief built into it. So that's nice. You're going to build this. This is why we built this is part of the reason why we built a non-thread safe version of the hash table before. There's going to be more about read locks coming soon. That'll come 2 lectures from now, so you may want to wait for that or dig into read-write locks. Like I said, this is also a standard Java feature, so you're free to press on if you'd like. Another thing that I like about this problem is very, very naturally, in a totally non-contrived way, you have to deal with balancing the load of your threads. If you were looking for, we talked about, again, in the video where I break down SARS-CoV-2, there's just sometimes when you're reading it, a lot of times at the beginning there's an error, at the end there's errors, and at the centromere sometimes in chromosomes, there'll be errors. Sometimes they'll just be errors, right? They don't know whether, well, this might be an A or a T, I'm not sure. And so I've split up the full chromosome data into a series of sequences that are the consistent part. And one really easy way to parallelize it would be to say, all right, just make a task per sequence. It turns out the Y chromosome has 50 separate sequences. So you're like, oh, 50 tasks, that's perfect, let me do that. But if you look at the length of these slices for the Y chromosome, this is one that I pulled from the NIH. There's just like, this one is 5-6 million long. This one is 9 million long. This one is 4 million long. Just the sequences, is that right? I think that's right. Yeah. There's a couple that are long here, and then all these are basically almost zero, right? And so if you had 8 processors and divvied up the work per thing, you just spend forever waiting for these 3 guys to finish, right? So the other 5 would just eat the rest of these tasks, and then we'd sit around and wait for this. So we're going to build something that slices up the big ones, right? Now we don't want to slice, let's say we were like, all right, fine, let's split everybody up into 8 slices. Well, I don't want to slice these little guys down here that are basically a couple of bases long, right? Those can all be their normal length. So what we're going to do is come up with some threshold that says, all right, split it up such that you get a nice healthy number of good chunks of data. It's fine to have all these be tiny because some threads will just eat those, or just like some of the tasks, those, it's fine to just put this whole K-mer in here, these tiny ones, the 45 or 40 or so that are just just really tiny. It's fine to just leave them as they are, but these guys we want to break out. Okay, so you're going to build threshold slices. There's some information here as well as a video, which I will discuss in a second. There's a couple of parts of it. One, you're going to slice things up. You're going to pass in the original unsliced data, the min and the max. This is a lot like our indexed range before, except we don't need the index anymore. And I cannot state enough that, like, I try very hard to like point out to people, I don't do anything to this data. So the original chromosome, when it gets sliced, nobody is going to like copy it into anything. You're going to get the original unsliced data and then go from min to max on that data. Don't expect this to be a copied smaller version of it or anything. It's just the original byte array. There's also a video that covers, we're going to not go from min to max on this array when you're dividing it up. So don't build it this way. We're going to go from, we're not going to do that one. We're going to do min to max on the offset range. And this video is shot with the hope of making that more clear. So definitely watch this. It actually is linked from the wiki and from the first bug JUnit test in your repo. If you fail that test in a certain way, like if you're trying to do the whole thing like this one, it will point you to this video. So definitely watch that video. I'm going to cruise through it because it already does that, but watch that video separately. Another thing I'd like to talk about is that this is an actual problem where you can optimize the code better than just the compiler can. One of my favorite computer science quotes is premature optimization is the root of all evil. That's from Don Knuth. And the exception in a lot of ways proves the rule. First of all, so we're going to build something called threshold calculation first, as a bonus part of it. I should switch this order of these slides. I'm sorry that happened there. So let me move this down. Just to finish out the threshold situation, is that there's 2 parts of it. One is you're going to actually slice up the data. The other is you got to figure out, are given the number of the amount of data I've got to process and how many processors I have, and I'm shooting for 2 to 10 times the available processors, come up with a nice threshold for it. So the details of that are on the wiki, but that's the second part of the threshold situation. Moving on to the optimization part. So this is the quote that everybody knows. The actual quote is much longer and more sophisticated. It talks about how it's the root of all evil like 3% of the time. 97% of the time it's premature optimization. What I'll point out is that this whole quote comes from 1974. This 3% number where he's saying like premature optimization is real is much, much lower now. Like the majority of the time when people are writing optimized code, they're just writing code that the compiler could do a better job optimizing it anyways, and they're just making harder to read code. And so a lot of the time it's just better to write clean, beautiful code that has good algorithmic properties, and then let the compiler go at it, and you get much better code anyways. Now, this is the sort of situation where you can actually outperform the compiler. And what I'm going to encourage you to do is focus on your algorithm. But if you're interested in optimizing this process, you can hop onto office hours or talk to one of us. There's ways in which to just really, really improve the performance of this, both from just bit shifting when you're surprisingly just packing the k-mers into the ints can be a huge amount of the cost. Another version is that you can build a concurrent data structure that's optimistic. That'll be much, much faster than the concurrent hash map that you built. So there's a lot of opportunity to do that sort of thing if you're interested. I will say that admittedly, I'm giving admittedly conflicting messages here. I'm like, focus on your algorithm and don't worry about this. And then I'm like, pack your byte array into an int at the same time. So try to find a healthy balance both in this class and in life. There you go. So this is the path to victory. I would say build the hash map warmup and the concurrent parallel version of the warmup that goes string to integer. Then I would build the threshold slices. There's two parts of it, like I said, slicing it up and figuring out a nice threshold. Then I would build a long concurrent map k-mer counter. Like you're going to pack in the k-mer into a long, and just it'll look a lot like this one. Excuse me, except it'll be a long. Then there's the inarray one. We're going to have an atomics lecture coming soon, which you may want to wait for, and then build the atomic integer array one. Then we're going to have a read-write block lecture, and then build a concurrent bucket hash map. And then you should be all good. So just sort of historically, historically when with the k-mer counters, once you get one of them, usually they all fall, right? So it's a good idea to build the warm-ups because once you've got the string concurrent hash map, the other ones will sort of be very easy to build, I would say. A lot of times people forget to balance them. The whole point of this threshold slicing is to make sure that you call them for your parallel ones. There's no need to balance a sequential one. The whole point behind doing threshold slices is to spread the load on multiple processors. The sequential ones, like the int array, there's no sense in slicing that up. But the parallel ones, you definitely want to. And the last one is that building the thread safe map, you have a lot of preparation for this. We made a non-thread safe map earlier in the class. It's surprising how many people, when they get to this point in past semesters, it's like when we were talking about this, it's like they had no idea what a hash table was. So I'm not sure what to say about that, except I need to do a better job. But recall that you're now building a thread safe version of something that you've already built a non-thread safe version. And with that, I'll say good luck and have fun on this assignment.